a lot. Do you have any questions or anything you would like to focus me further on?
One thing I'd like to do is...
Excuse me, before we continue with questions, can I just change the tape real quick, please?
Yeah. Need to elaborate more. I think we have a lot of more time.
I'm waiting for Malarka to get done, but I've got one for you.
Go ahead.
Can you go into why the fine structure constant, the Sommerfeld constant, was considered such a huge breakthrough, and why it affected both the physicists and the people who believed in a more spiritual kind of a thing? Why it was kind of a nexus number? What was so great about 1/137?
Oh, that's a good question. So I cannot answer the question why it would be important for somebody out of science. What is let me perhaps start from a wider perspective and then coming back to that constant.
And if you get stuck, I can answer. I just wanted you to talk.
Yeah. So what does it mean, those constants? Right now, in the current understanding of science, or in particular physics, so quite often when I say science, I mean physics because of my own limited perspective, there are four interactions or fundamental theory. Gravity, the electromagnetic interaction, the weak interaction, and the strong interaction. So gravity, everyone is familiar with gravity. If I now would put my phone and would fly on the ground, the reason that the Earth is rotating around the Sun is moving in the galaxy, and the galaxy is moving in the huge universe, that's all due to gravity. Gravity is responsible for the structure of the universe. And if we look up in the sky and we see those stars, these stars are all suns, which some of them might have a planetary system, then they all move and there's all force between them, and this is all gravity. Electromagnetic interaction, that is, for instance, light. That is, for instance, the reason why this is something that's called the Pauli principle. Why certain atoms have a repelling force with respect to each other. Electromagnetic interaction is of course electric current, is of course magnetism, which is very important for electronics. I mean, our whole world is nowadays dominated by software, but software runs on some kind of computer chips, which is all electronics, and this is all electromagnetic interaction. The weak interaction, that is, for instance, the decay of particles, but this is also responsible for all the processes which happen in the sun, which generates energy. And the strong interaction, that is the force which bounds the quarks and neutrons in the atomic nucleus together, and they all have a different properties when it comes up to their strength. The world we are living here, this is really dominated by electromagnetic interaction. If the world would be dominated by gravity, then we would be all spheres, because with respect to gravity, that would be the preferred shape. But we are not spheres. The reason that we have that we look like that is because the electromagnetic interaction is stronger than gravity here and gives us this upward shape. Now, the reason that we have mountains, this is also because the electromagnetic interaction is stronger than gravity. Gravity would only take over when mountains get too large, because then they start to melt. But apart from that, it's the electromagnetic interaction which is able to somehow, which is stronger than gravity. And the weak interaction has the name because it's very weak, and we can be lucky about that, because that's the reason why our sun will last billions of years, and not only a few million of years, because if that would have been happened, then the sun would be already burned out and he would not exist here. So the remarkable thing about all these fundamental interactions is actually that their properties are exactly arranged in a way that allows us to exist. And our world is exactly that, because there's a certain interplay of all these forces. And now coming back to the question about the fine structure constant or Sommerfeld constant or electromagnetic constant, that term 1/137, this exactly determines this exactly determines the strength of that interaction. So therefore it's important in science. Another fact that I would like to, which is interesting about that, it goes back to the understanding of Greeks and numbers. So the Greeks saw that the nature is built of natural numbers and the ratio of them, and not of real numbers. So this fine structure constant is really in very, very good approximation 1/137. So this again is remarkable, because it's exactly what the Greeks wanted to have as an understanding of nature. But the other aspect of your question I cannot answer.
Okay, well let me see if I can poke you in that direction. So Arnold Sommerfeld was working with Einstein's equation E equals mc2. You don't have to go into the equation that he developed it into, but what's important in that equation, which is not hard for anybody here to really understand, there are three constants, okay? And I think there's a beauty in those constants. I've always been particularly in awe of the Planck Constant and anything that is so small, just the concept of how tiny this thing, the smallness of that. So there's good analogies in the book about how to compare the size of this, the Planck length. And so basically the Planck length represents 4 feet. If everything else is as big as, it's just like this incredibly infinitesimal kind of a thing. And there's these three constants in the equation that Sommerfeld's using. And the fine structure constant, when it's inserted into the equation, because everything else, all the other constants are known, but when it's inserted into there, everything magically changes in a neat way. And I think that's one of the things that Pauly was so struck by, that whole thing. It's just amazing how it comes into this pure number and makes everything in the universe kind of fit together. And what he was saying was that if it wasn't this precise number, if we were off like 4%, everything that we know, the carbon that you were talking, everything we know would change. Life would not be possible as we know it. It's really, but because it is that number, everything is possible. It's just kind of, it is scientific, but it's also very deeply spiritual and powerful. So,
yeah, this is just one of the questions nobody has an answer for, why it's exactly arranged in that way. And this is then also exactly the moment where for a lot of persons magic or some higher existing like God or something comes in. There are other approaches. There's, for instance, David Deutsch, that's a UK physicist. He has this theory of multiverses. So he just said there's just an infinite number of universes, and just by accident there's one where everything works out nicely, and that's our one. And that's a perhaps very cynical approach to that. If we of course want to give us more meaning, and then we might say, oh, there might be something behind that arranged everything exactly like that, which might be a scientific principle, which might be something which is a not scientific principle.
and finding a number as powerful as this fine structure constant really grew out of a process that you mentioned, Kepler's obsession with the number 4. There was another alchemist of his era, I believe his name was Flood, who argued with Kepler, no, it's 3, no, it's 4, and they determined, and Pauly determined, that there's a flow in the universe in these numbers. So you have unity, you have 1, but you go to this 3 and the 4 thing, and that leads to this fine structure constant also. So And we're kind of proving that Kepler was onto something, even though he had no clue of any of the things we're
Yeah.
talking about.
No, Kepler was quite, I mean, this is something which happened at the beginning of the 20th century with Einstein's special relativity, that we suddenly understood that the 3, which was so important in physics, was changed by the 4. So that was exactly a revolution what happened. And what does this mean? There was this old idea that there is something like absolute space. So I mentioned before when I started that in science it's important to measure, and your measurement should be, you need to report your measurement in a way that you can transform it in somebody else's measurement. The simple example is you have, you are in a car and you are driving and somebody else is coming towards you. Of course, in your world, you are driving and that person is coming towards you. In the other car, that person sees that you are coming towards him. But it's of course obvious that it's very easy to transform from one system to the other system. And this is very important when speaking about measurements. The measurements must be done in a way that you can say, okay, somebody else, an observer which is somebody else, an observer which might be, for instance, traveling with a certain speed, how he would see what you are doing, because the physical laws, which are fundamental, or the fundamental understanding of nature, should not depend on where you are as an observer. It should be invariant of that, and therefore these transformations are important. And the transformation which persons worked on was a Galilei transformation to say, okay, I go from one 3-dimensional space to one other 3-dimensional space. And 3-dimensional space is what we are used to. That is just this room. It has one dimension here, one dimension here, and one dimension here. And so we can describe the volume of that room. We can calculate that and we can describe that. So this is where the 3 is coming from. But what Einstein, and then around the end of the 19th, beginning of the 20th century, persons said that all questions in physics are answered. That bringing up Max Planck, who was a well-known physicist and has his own constant, the Planck Constant. Then he started, so when he was young, he went to academia and said, what should I do? I'm interested in study math, I'm interested in study physics. And then somebody told him, why would you spend your time with physics? All the questions in physics are answered. We understand everything, and do something else. Luckily, Planck stood in physics, and those persons were completely wrong, because we don't understand everything. We hardly understand anything. And the important thing of Einstein was that he realized that when he traveled very, very fast with the speed of light, then we cannot treat time and space independent anymore. And instead of working with 3 dimensions, we need to work with 4 dimensions. We need to also take the time into account. And this was around that time, this was also the era of Pauli. This was somehow the real revolutionary change. And that was why Einstein was then getting really, really popular, because Einstein had the guts to say to everyone, no, what we are doing is wrong. Everything makes sense when we change from 3 to 4. And he did not invent anything. He just saw what is already there, what other persons did, Lorentz, Minkowski, Mach. He just put that together, shook his hand and said, guys, you're so wrong. If we just change that, we just make the simple change, then everything makes suddenly sense, and a complete new era of physics emerged from that. That is one of the reasons why Einstein was such an outstanding physicist. And this is where suddenly those numbers come in. The number 3 is a very middle-aged number, because it's of course Trinity, which is very important in basic Christian religions. 4 is a very interesting number, because it's what was important for Pauli was duality, and 4 is interesting because 2 times 2 is 4, 2 plus 2 is 4, and also 2 to the power 2 is 4. And these are just the basic mathematical operations. So if you just combine 2 with duality in any arithmetic way you can think of, you add them up, you multiply them, or you just take them to the power, you always end up with 4. And therefore they were so fascinated about that. And because also at this time there was this huge revolution going on in science.
And also the fact that in gematria and number mysticism, the first 4 numbers, prime integer, 1, 2, 3, 4, add them up, it's 10, which is always reduced to the unity, it's 1. There is a very power in the first, the universe is contained in those 4 numbers, and 4 is the last of that, so that's part of the mystical thinking on all that. I think one thing, because you haven't mentioned Niels Bohr today, right?
No, not yet, yeah.
I think one of the interesting distinctions between, not to pick on Germans, because I'm German too, but one of the distinctions between the German physicist way of thinking and maybe Niels Bohr, who was Danish, is they said the Germans were all about calculation, mathematics and calculation. They were very focused on that, and it had to be able to be reduced to numbers. And Niels Bohr made some of his breakthroughs, I think, because he had a different approach to physics too. And they said the Danish, in Copenhagen, Niels Bohr's team of physicists were more about thinking and intuition, which is kind of woo-woo. Numbers are hard facts, but this thinking and intuition that made some of the leaps was harder for some of the German school of physics to handle at the time, yet they really respected and revered Bohr's work. So you want to talk a little bit about Bohr?
Yeah, let me first defend Germans.
I knew you were going to do that!
So, Niels Bohr was working with a lot of remarkable persons, like for instance Heisenberg, Weizsäcker, and also Pauli, and they were German or Swiss. So there was a lot of and then at a certain moment they had a conflict with some very weird guy from Austria, Erwin Schrödinger, I think the most important point about that is that around that time, whole science, all the developments were happening in Germany and German-speaking countries and the borders, like Denmark, Copenhagen, where Niels Bohr is. And then all of them left during World War II or before World War II. Niels Bohr needed to leave because he was Jewish, and he got the Weizsäcker family. So the father of Karl Friedrich von Weizsäcker, he was a member of the Nazi party. He was a diplomat for them, and so he had some connections. And Bohr got told that if you not leave now, you will end up in a concentration camp. So they really did during the night a spectacular feat, and he only received this warning because he was so famous, and he was and he had powerful friends in Germany. They all had, so for instance, speaking going back to Niels Bohr. Niels Bohr is also a person who is considered a real genius. So even among those geniuses, everyone looked up to Bohr. There's a funny story about that in Feynman's autobiography, because Niels Bohr and his son, also famous physicists, they arrived at the Manhattan Project, and nobody dared to say any against them, because genius. And then Feynman at a certain moment made a critical remark, and so Bohr was really so happy that there's at least somebody who questions him and it's skeptical about that. It's also Niels Bohr was also one of these persons who said, okay, he's so good, everybody agreed with his personality, which was a little bit weird. So there was somebody running in Copenhagen and looking for a police officer. Around this time, the police was still walking around, and said, there's somebody breaking into that house, there's somebody climbing around that building, you need to do something. So the police was running in order to get the thief. They said, no, that's just Professor Bohr, he is just training climbing. So this is what they all like to do. They not did Niels Bohr and his team. They did not physics by sitting in a desk. They had a lot of discussions while trekking. They had a lot of discussions while climbing. They had a lot of discussions while skiing, because they found their inspiration. So what is Niels Bohr legacy? And this goes now back to light and waves and particles, which is just written here at the beginning of that. We have atoms, and when you study the spectrum of atoms in light, you see that you don't get light out of them. They don't absorb or emit light in any frequency. There are just special frequencies, and persons try to understand that. And Niels Bohr had this idea that these electrons in the shell, they are in certain states, and they can only move from one shell to the other shell. And that reminded him on the planetary system. So they described the very small world like a small planet system. And as they had no idea how the small world was interacting, they said, okay, we know from our world that there are certain symmetries of the fundamental laws, and we now need to construct the small world in a similar approach. And that was the beginning of quantum mechanics. And the success of Bohr was that it was something which nobody else perhaps would have dared to do, but it was so successful because it had the right answer, and it really studied a complete new approach to physics, which was quantum mechanics and quantum theory. And the remarkable thing about that is that it's suddenly you have a theory for something which we as a human cannot anymore observe. I mean, the Bohr, this is something which we are familiar with. We can see the sun.